I'm coding an LLM from scratch, and today I'm gonna be learning, and we are gonna be learning a lot about kernels, mega kernels, combining multiple GPU operations into a single big operation and doing it parallelly so it's a lot faster. So creating your own GPU CUDA or Triton kernels in theory and all of the theory about it. In the next video, we will also learn how to code it. Watch this to learn how to make your AI projects, LLM projects, or any other computation projects in Python compute a lot faster. What is a kernel? A kernel is a function that runs on the GPU. When you do a PyTorch operation like matrix multiply or ReLU, under the hood, PyTorch launches a GPU kernel to do that work in parallel. For example, torch.matmul A and B matrices, and we get the output. This line launches a matrix multiplication kernel on GPU. Why kernels matter? GPUs have thousands of tiny cores. To fully utilize them, we must run lots of work in parallel via kernels. Avoid slow memory traffic, because we need to push data between those kernels within the GPU between different kinds of processing units. Avoid launching too many small kernels, which wastes time. The problem with many small kernels. Let's say your model does the following in the forward pass. Linear layer, so this is general matrix multiplication. Then activation function, let's say SILU. Element-wise multiply, add residual, and normalize, let's say RMS norm, for example. This is just implementation of the function. These are the functions in our code. Both are chunk of code. Each of these could launch its own kernel. That's 5 kernel launches, 5 reads from memory, 5 writes to memory. Too much overhead. The GPU spends time moving data around instead of computing. So reading for this, sending to this, and then reading, writing for this, and then same for this, for this, for this. So what is this idea of mega kernel or kernel fusion? A mega kernel, fusing several small operations into one large kernel. Instead of kernel A being mat multiply of x and w, the weights, and then kernel B is passing the output through silo activation, and then kernel C is multiplying with some z. So that could be this element-wise multiply here. You write one kernel that does this mat multiply and then silo and then z. So this reduces memory traffic. Data stays in registers shared memory. No need to move back and forth and then read and write. Kernel launch overhead. So just launch this one kernel. And wasted parallelism. So wasted parallelism happens when a GPU could be running many operations at once, but it doesn't, due to poor kernel design, small workloads, or inefficient data access patterns. Let's break it down here. What parallelism should look like on a GPU. A modern GPU like NVIDIA A100 has thousands of CUDA cores. Each core can run threads in parallel. The goal is to keep all cores busy all the time. If you give it a big enough job, like a large matrix multiplication, the GPU can schedule tens of thousands of threads to run simultaneously, doing small pieces of the work. So what is wasted parallelism? It's when GPU has lots of compute power available, but the kernel doesn't create enough work. So we had a simple kernel, just simple matrix multiply or simple element-wise multiply. The work is too small or split inefficiently. Threads sit idle or do trivial work. This results in underutilization utilized hardware. Slower execution, even though the GPU could have done more and faster. So that's wasted parallelism, or wasted GPU resources on too simple tasks, inefficient tasks, etc. Common causes of wasted parallelism: small kernel launches. Each PyTorch operation, like x plus y, might launch a separate GPU kernel. If the input is small, the kernel runs on just a fraction of GPU threads. Example, adding two 64 element tensors, that's just 64 threads. On A100, that's like using 0.001% of the chip. Yeah, so just 62 elements. The two 62 element tensors, just adding them, it's using just a little bit of the chip. So this operation is too simple, too small. So we are not utilizing the 100%. You want to utilize 100% of the kernel, of the chip, and the kernels within the chip. Then fragmented work. If you break a computation into many small steps, for example, normalize, then scale, then add, then activate, each one may not fully utilize the GPU. And then thread divergence. This is the next common cause of wasted parallelism. If threads take different execution paths, for example, from if-else conditions, the GPU can't run them all in parallel efficiently. Some wait while others work. Poor memory access patterns. If threads read-write memory in a scattered or unaligned way, memory latency increases and bandwidth drops. Again, cores may stall, wasting parallel potential. Because threads are reading and writing memory in a way that's not aligned with each other, then some threads or cores need to stall and wait for the others to read and write memory, to process data, to give them data. So why it matters for any LLM, and including this LLM that we are coding from scratch? So transformers involve giant matrix multipliers. This is great for parallelism. Many tiny element-wise operations, like residual norm addition, RMS norm, etc. This is bad for parallelism. Layers like RMS norm, rope, residuals, lots of small steps. Yeah, this was the example. RMS norm is a bunch of small steps. Each of those tiny operations runs its own kernel. You end up with lots of GPU kernel launches doing small work. That's a wasted parallelism. You can combine these small operations into one big operation, and then that will run parallelly on the GPU. It will launch threads parallel. It will utilize a lot of the 100% of the cores, or close to 100%, if the operation is big and complex enough. So we can fix it with mega kernels. By fusing multiple steps into one kernel, you keep data on chip in register shared memory, so no need to read data, transfer it to the chip, and then do some calculation, and then write back, and then read again, do another calculation. So you read once, do all of the calculations, and then just go back. So no this bandwidth bottleneck. Create larger workloads that can fill the GPU. Reduce thread divergence, so threads are working more closely with each other and producing data each of them needs, so they don't need to wait for each other too much. Maximize GPU utilization. This turns wasted parallelism into productive parallelism. And rule of thumb, the GPU is fast only if you give it enough work in the right shape all at once. Wasted parallelism is what happens when you fail to do that. So enough work, so a lot of work in the right shape. We need to take care of that, and all at once. So let me scroll back up and let's continue. So we got here to wasted parallelism. Yeah, here. So this is the end of number 4 here on top. I'm gonna leave this chat below so you can self-study or copy this or continue the chat with ChatGPT. I will also leave the prompt if you cannot use ChatGPT, so you can just generate tutorial for yourself. So how this applies to Llama code? In this instance, I'm analyzing Llama code, but we're gonna use this for our LLM. So how does this apply to our LLM as well? So we will walk through components of Llama to see where fusion and mega kernels could happen, but Llama is similar to our LLM, so we will be able to apply that to our LLM from scratch as well. So linear layer and nonlinear. In transformers, these are everywhere. So Q projection, key projection, value projection, output projection, up, gate, down, LM head, So up and down are from the, mixture of expert or neural forward pass, and gate, I guess it's from mixture of experts. These are all general matrix multiplication kernels optimized via this QBLAS. So this is the CUDA optimizing software. So fused query key value. So you know that each of these projection matrices, they all have same input, which is the hidden state for the token. Because they have all same input, you can fuse these three together. So you can say matmul hidden states and stacked query key value weights. So you can just concatenate them. So you see, just you create one array. The first third is, or whatever, the first part is key, second query and values. And then you can just separate them after the matrix multiplication. So here this matrix multiply will have a bigger matrix multiply. It will do it faster in one kernel. This is what DeepSeek does. They have a bunch of these, like these stacks in the code. That's one kernel instead of three. And then the attention kernel. So in the attention mechanism, you have a query key matmul, scaling, masking, softmax. This is attention weight multiply. So you can fuse all of this, but it's already actually fused in PyTorch 2.0 plus. So they already made a mega kernel for this because it's a very common operation. So it's this one, it's f.scale.product attention. So you can use this, and these people that code this are very good. So you can just use this because it's probably as optimized as it can be. But if you have different architecture here, maybe you can write your own kernel like this. So you would just create some matrix multiplication or another way. So let's see how we can do it, how we can write our own fused kernel with Triton or CUDA that performs the full attention computation instead of using this scale.product attention. The goal is to compute attention from scratch. So we have a query key value, and this is the matrix. So we have softmax. Actually, we start from here. So query times transposed key, then divide by square root of this dimension here, and then softmax of all of that, and then matrix multiply that with the value. So we have a bunch of these. I just explained it here. So naive way would be just to calculate it step by step. You see? So each calculation is going to be a separate kernel. So we will have general matrix multiplication, element by scale, masking, softmax, and this. Goal of custom kernel. Instead of 5 kernel launches, you'd write one fused kernel that does all of that. All inside shared memory or registers, so no slow global memory reads, writes between steps, because these global memory reads and writes can be a bottleneck. If you have fast processing, fast computation, then memory reads and writes and sending the memory can be the bottleneck. Implementation approaches, you can write this with Triton, best for high-level custom kernels, easily integrates with PyTorch. So Triton allows you to load query key value blocks, compute attention in a fused pass, efficiently use shared memory, and warp level parallelism. So these are example projects: Xformers, Flash Attention, Megatron, LM's fused attention kernels. So Triton is simpler to use than CUDA. CUDA is more low level. And the performance, I've heard Triton is just a little bit more less performant. So you want to do everything in Triton, especially when you are testing and experimenting. And you can keep Triton all the way for everything. Or if you want, and what DeepSeek does, just to squeeze a few percentage more performance, they code everything in the end, they change to CUDA. So it just makes it a few percent better. And it's also complex to code in CUDA, more complex. So if you are doing maybe large scale deployment, so a few percent would mean a lot for you, then you can, in the end, after experimentations, convert from Triton to CUDA. So CUDA, more flexible but lower level. You must manage thread block grid structure, share memory manually, so this is done automatically in Triton. Warp level reductions for softmax, load store coalescing. Never heard of this word, but anyways, so it's more manual for a bit more performance. I recommend using just Triton. And then bonus trick that flash attention does, so instead of loading entire queue and query into memory, they load chunks or tiles and then just process calculate them. So this is gonna dramatically reduce memory usage. So if memory is your bottleneck, you can use this trick. You can ask this to ChatGPT to explain further and give examples if you're interested. Let's code a simple kernel. So we will import Torch, import Triton language as TL. So here I have some code. This could be a bit too complex for this tutorial, but I think I can explain most of it. And if you wanna learn more or implement this into your own code, then first of all, you can ask self-study, say, ask AI to help you create or code a kernel for self-attention. You can also screenshot this or click the link below to get this code. Okay, so here I will explain it. We will mark the function. So this is a plain Python function in Python, but we mark it with Triton just in time. So it's a Triton function. Here we have pointer to query key and values in memory in and out. Let me scroll down. We have good explanation here what each of these functions does. So TL, so Triton language, dot program ID 0, determines which style of queue this kernel instance is processing. So as I said, we are loading by tiles, by chunks, so we reduce the memory bottleneck, and we will just have more computation, but since we already have a lot more computation than memory, then we will just use more computation. Okay, and then tl.load load slices of query key value from global memory into registers. So we will use this to load. So this is gonna be tl.product query and key and transpose B. So we want to transpose this key matrix. And then logits times 1 over square root of D, apply scaling factor from vanilla attention. This is the vanilla attention. Then we have these TL max, TL exp, TL sum. We need that to calculate the softmax and numerically stable softmax. So, for example, there is no division with 0. This will deal with if there is any divisions with 0. This will deal with it. By, for example, instead of dividing by 0, it will divide by 0.0001, like some small positive number. Okay, and then probability. So this is the classic computation, and then this is for storing, tl.store, store into global memory. So here we have program ID. We start from 0, and then offsets for current queue block. So we need to calculate for each tile, each part of the query block, how much to offset in the memory, so we can get, so where it is in the memory, offset N, offset M, M and D. So this is a bit confusing as well. I'm gonna be practicing more in one of the future videos when I try to implement this kind of stuff into my LLM. So I'm gonna skip it for now because it's more confusing, it's more difficult for me as well. But we see here we create the matrix of zeros, so block M, block N. So I guess block M and block N is just if we have matrix for queries, M would be like how many rows, this small part, how many columns is for N. So we take this small matrix out of the big matrix. So that's what this offsetting would be. But this is more complex, so I'm making videos every day trying to understand this, so you can also watch with me and self-learn. Actually, my next video will be coding, but learning how to code this from simplest tasks, just maybe some matrix multiplication, and then going more progressively. So you can watch my next video to learn more, like to have more practice in coding it, where we will code together. So next time we will try to learn how to do all of this code. That's it for today. Thank you for watching. You can check my other videos while coding this LLM from scratch. I'm documenting everything I'm doing and learning together. So, see you next time.